Hello everyone, I hope you all are doing great. So today we'll be looking into force on a current carrying conductor and the derivation of its formula. Very first you need to understand the concept of force in a moving conductor. Very first, we know that this is just suppose for a while magnetic field. This is the North Pole and this is the South Pole. Now what if I say that an electron is moving in this direction? Now this is basically a charge that is moving in the upward direction. Now what is the velocity of the direction? The velocity is this side. So according to the right hand thumb rule, if we want to know that what would be the direction of force, so right hand thumb rule. For the negative charge, it becomes left hand rule. So we'll apply left hand rule that says that in the direction of the electron moving, you have to keep your thumb. Now if you keep our thumb in this direction, all of our four fingers will be in this direction, right? Now this is what this showcases us the direction of the magnetic field. This is the velocity, and this palm shows us the direction of the force. Now how we have done this? Now you all know this is called the y-axis, this is called the x-axis, and this is called the z-axis, that is out of the plane. Now this is a moving charge, this is the electron. In this direction it is the magnetic field that is moving on. In this direction is the velocity of the charge, and in this direction it is the force that is acting upon the charge. On a unit charge, this scenario, the force is often calculated by a formula Q that shows us the charge, then V that shows us the velocity, and the cross product of B, that is the magnetic field. This terminology or this formula is used for for finding out all the force acting upon the body. What if I say that this isn't a single thing, or this isn't a single charge that is moving? Now we are talking about a proper, okay, let me redraw it. Or in a same circumstance, this is the magnetic field, and now a current carrying conductor. This is a conductor, this is one side. Okay, I think I should running it. This is a conductor, let's say now it is a conductor that is placed within this circumstance of the particles. Now in this conductor there are a lot of electrons or the charges specifically that are moving. This is the cross-sectional area or cross-section area of a conductor that is often termed as A. This is the length of the conductor that is denoted by L. This is the magnetic field that is denoted by B. This is the charge that is denoted by Q. And we all know that now we are talking about a flow of charge within the conductor. There isn't a single thing. Now here, what we did in our last thing, accidentally I have removed this all, but still what we discussed here was about a single charge. But here, we are discussing regarding number of electrons. Now this can be 5, this can be 500, or this can be 5 lakh as well. This depends upon the situation. But here at instance we are talking about only a single what we can say, this circumstance. So here we will consider I, that is equal to Q upon T, the number of charges that are moving per unit time within a conductor or a wire or a circumstance. This is called the current. So here we are considering the moving current. I hope that so far things are clear to you. Now, what usual definition do we have in our mind regarding the charge? It was we have to find out the force, right? So it's F is equal to Q V B sine theta. Here Q shows us one more thing. Q is often equated to N and E. Now N shows us the number of free electrons and E shows us the charge on electrons. So here whenever we are following up the Q and E, so we came to know about this circumstance, where small n shows us the density of the current that we will be focusing on. Now how we define the density? Density's formula is basically m upon v. Here we aren't considering mass, we are considering the number of electrons. So number of free electrons per unit volume. Now we all know what is the formula for the volume. Volume is equal to area multiplied by length, right? So what if I say that this is equal to A upon L, or N is equal to A upon L. Now on the place of this formula, can we put in the value of AL is equal to here? AL will equate, so after going there it will become NAL equal to N. So here in place of Q we could write small n AL multiplied by E, right? So here the formula will turn out to be F is equal to N AL E multiplied by, or let's just not consider it multiplied by, V. Velocity is equal to distance upon time. Here the distance is L. Since we are considering only this circumstance, so it will be L upon T into B sine theta. Now L, the distance is, displacement is vector quantity, B is a vector quantity. Since we have a proper direction for it, right? So we'll keep all the scalar quantities outside the bracket. So it will be like this. In bracket L multiplied by B, since vector quantities can be written in the form of cross product. Now here we can actually consider this all term as I. Since number of the terms, area, length and electron, these all shows us the circumstance of Q, since we can equate it as Q, right? So Q upon T, I've told you before, is equal to I. So we can directly write here I into L and B sine theta. So this is how we find out the force that are acting on the current carrying conductor. Thank you so much for watching. Stay tuned for future videos.